All right, so let's continue our discussion on trees. And so far we have looked at general trees, which means that the number of children is arbitrarily large, of course bounded by maybe n minus 1. However, many situations and many applications demand a fixed number of children. That is, there is a bound on the number of children. It not always be fixed. So such trees are also very common, and we would like to spend some time talking about those. Right? So in general, we can talk about a K-ary tree, in which the number of children is bounded by k, and the structure will look very similar to what we had for the um, uh, um, C++ representation of the arbitrary children tree, right? So this was our original representation for arbitrary tree. So this could also be used. I mean, there is no problem in using this particular linked list based representation, right? So if it works for arbitrary number of children, it will work for Kary tree also. But because you know that it is a Kary tree, you can do a little better. For example, you can have just an array. This is what we discussed earlier. And the children of k essentially is talking about an array of pointers to those nodes, right? And in a similar manner, you can have again a vector of all of this. So the same representation in case of C++ will work for Kary tree also. You could use a vector or an array, right? When k equals 2, which means that it's a binary tree, that also is quite common in practice. In such cases, you can either use children of 2, or you can just have left and right as 2 pointers inside that, right? So this left and right is kind of uh, used as a nomenclature, but and because that is how we visually depict the tree, binary tree. But you can give any names, that's not really an issue. But typically left and the right child, left and the right children are the ones that we will use when we are talking about binary trees. Okay, so given this, the representation, or I'm just going to show you pictorially how it will look like. A Kary tree will look something like this. In this case, it turns out to be a ternary tree or three-ary tree, in which case each child has maximum 3, each node has maximum 3 children. Uh, Binary tree might look something like this, right? So there is an arbitrary tree, and you can have maximum, each node can have maximum 2 children. So yeah, so I hope this concept is clear so far. There are some properties which are specific to binary trees which we can think about in terms of, let's say, the number of pointers or number of internal nodes or number of leaves, right? So now imagine only binary trees, right? So uh, each node has maximum 2 number of children, right? So for an n node binary tree, these are the properties which we are listing, where n is non-zero. What can be the maximum height of an n node binary tree? And what is the minimum? So for all of these questions, please think about it, note it down in your copies or online. And if you want to share, feel free to put it in the chat box, right? So I'll just discuss this. So what is the maximum height starting from, let's say 1 or 0, whichever you want to use? What could be the minimum height of an n node binary tree? Right? So if you pack everything such that you want to minimize the height, but you are not allowed to have each node containing maximum 2 children, then what is the minimum height you can get? How many null pointers exist, right? So if you look at the previous diagram, essentially all of these are null pointers, which means that this is a leaf, right? Similarly this, right? At the same time, you can as well have, for example, for assuming that there is this node here, 2 of the children of this node are null, right? So there are certain number of null pointers which exist for yeah. So if a node has both the children, then it has zero number of null children. If it has one child, then it has one null pointer. If it has no children, then it has two null pointers in case of a binary tree, right? So I would like to count these null pointers, and that plays some role in proving certain properties, and that's why we are interested in those null pointers. Um, how many minimum number of leaves could be present in an n-node binary tree, and how many maximum number of leaves could be present in an n-node binary tree, right? So these are the questions that we would like to think about. So please spend time on this. Let's discuss the first one first. What is the maximum height you can get? Okay. So this seems to be reasonable because we have starting from 1, if we assume the height to be starting from 1, then we have a linked list of nodes essentially, which means that every node other than the leaf has only one child, and then that will turn out to be the maximum possible height you can get, and therefore it will have n as the height, right? So that seems to be appropriate, as Abhishek, Shania and Murari have suggested, right? Anybody wants to argue against that? Okay, so let's talk about the minimum height now. Okay. Chania says log n to the base 2. Murari says log n. Where is this log factor coming into picture here? We are talking about binary trees where there is n. Where is this log factor coming into play? Shania says kth level has 2 to the power k nodes, right? Murari says split. Okay. Abhishek also says log n to the base 2. Okay, so we know that log and exponent are opposite functions, right? Log of e to the power x is x, right? So log and exponent in some sense cancel each other, similar to plus and minus in some sense, right? So if you look at the number of nodes at every level, right? So since you want the minimum height, you want to have maximum number of children at every level. So the first level will have just the root. Then the second level can have maximum 2 number of nodes. The third level can have maximum 4 number of nodes, and so on, 1, 2, 4, 8, like that. Exponentially, the number of nodes is increasing. And therefore, if you have, let's say, k number of levels, then you will have 2 to the power, in some sense, order of 2 to the power k, maybe 2 to the power k minus 1, but that is exponential in 2, right? And therefore, the number of such levels is going to be log of the number of nodes, right? And therefore, the minimum height that you can achieve is going to be logarithmic in terms of the number of nodes in the binary tree, right? So that also seems to be all right. In case somebody has not understood, feel free to ask. So this is very similar to the binary search representation, right? So we were going in the opposite direction where we wanted to search in n. Once we find the middle element and compare, we can discard half of it, and therefore now we have n by 2. Then we have n by 4, n by 8, and so on. So we are exponentially reducing the search space, and therefore in log n steps, where n is the number of elements in the array, in log n steps we are guaranteed to reach that element, assuming that the array is sorted. In a similar manner, we are going now in the opposite direction. The way we counted, we have 1 element, then 2 elements, then 4 elements, then 8 elements, right? One can argue that actually what we are talking about is number of nodes at a particular level, but are we talking about the number of total number of nodes? Well, the total number of nodes is just going to be twice of the number of maximum number of leaves that you have in a full binary tree, right? So this kind of a tree where each node has two children is called as a complete binary tree. And except for the last level, it is called as a full binary tree. So if at the last level one of the nodes has only one child, then it is not called as complete, but it's called as a full binary tree. All the internal nodes will be full. So that is, they have two children. Okay, so how many null pointers exist in this n node binary tree? Will it always be fixed? Will it be some specific function of n? Any suggestions? Okay, Abhishek says it will vary. And that can be seen, right? So if you take these two extreme cases, linked list based representation, right? So it has n minus 1 for the internal nodes, the null pointers. And then the last one will have two pointers, null pointers, right? So it will have n plus 1 pointers. How about kind of complete binary tree, which is kind of having minimum height, right? So in that case, the number of leaves is are the leaves are the ones which are the only ones which have null pointers, and the number of leaves is going to be, let's say, n by 2, and therefore the number of null pointers is going to be approximately n. So that seems to be different from n plus 1. So that although the values are a little different, that does also give some indication that it is going to be very close to n. So let me ask you in this manner. Can you construct a binary tree having n nodes which has less than n null pointers? Or can you construct an n node binary tree which has more than n plus 1 null pointers? Okay, so it doesn't seem to be that anybody is able to construct that. Okay, so we'll discuss that. How Murari says it should not vary, because if we consider null pointer also part of the tree, then total edges will remain constant. Okay, that seems to be an interesting argument, right? So you have n nodes, right, and therefore you essentially have 2n minus 1 pointers, right? No, sorry, n nodes will have 2n pointers. Outgoing from each of there will be 2 pointers outgoing from each of these nodes. Since we said n nodes, 2 n pointers. Out of these, n minus 1 nodes are going to have a single parent. N minus 1 nodes have a single parent, which means that you are going to use, out of these 2n edges, n minus 1 edges are gone, and therefore what are left with is essentially n plus 1. And therefore Murari's argument is correct that you will always have a fixed number of null pointers. The reason why I gave that example of you have this logn number of n by 2 number of leaves, that has a small rounding error, right? Because if it's a complete binary tree, then you will have ceil of n by 2 number of leaves, and n by 2 minus 1 number of internal nodes. So there is a small rounding error that happens there. because of which it's actually going to be not n but n plus 1, right? So if it is even number, then it is going to work out fine. If it is an odd number, then it is going to create a rounding error. Good. Thanks, Murari, for that. How many minimum maximum number of leaves could be present? So how many minimum number of leaves could be there? One, right? So in our linked list kind of a tree, we are going to have just one leaf, right? Everything else is going to be internal node. So as Shania, Murari and Surya Narayanan say, that is going to be one minimum leaf, and the maximum number of leaves you can have is, Naimisha says n by 2, right? Max of ceil of n by 2, Kasibhatla says, and minimum 1, right? So that seems to be reasonable, that if you have a kind of complete binary tree that is having minimum height, then you will have maximum number of leaves to be n by 2, right? So that gives us some indication that what kind of trees you can construct as a binary tree. And some things vary, right? So the height can vary, the number of leaves can vary, but some things remain the same. For example, the null pointers. Okay, that sounds good. So I'll just mention that here. Yeah, that 0 or 1, I think we should consider it to be 1 for the minimum, not 0 really. And then n by 2. Okay. So what is the maximum number of nodes a binary tree of height h may have? This is a kind of a reverse question, but I would like to ask it in terms of the height. Two to the power h plus 1 minus 1, Kasibhatla says. I see. So height is starting from 0. Naimisha says 2 to the power h. 2 to the power h minus 1. Okay. Mrityunjay says 2 to the power h minus 1. Yeah, so approximately the order is going to be exponential in the height, that we all understand, right? It's just that the exact number is going to be decided by whether height starts from 0 or 1. If it starts from 1, then we will have to do h minus 1 something. But if it starts from 0, then that is going to be 2 to the power h. Right? So yeah, I'll use your function 2 to the power h minus 1. Note that this number is not going to be power of 2, right? It has to be 1 lower than that, right? So you have one node at the first level, which is 2 to the power 0. That is okay, but it can actually be viewed as 2 to the power 1 minus 1 also. But the second level will make it clear. We have 3 nodes total, then we have 7 nodes and so on, right? So it becomes 4 minus 1, 8 minus 1, 16 minus 1, like that. So therefore, this is going to the power h minus 1. Full nodes, that is the nodes with 2 children, right? These are also called as full nodes. How many minimum number of full nodes can be there? How many maximum number of full nodes can be there? So what is the minimum number of full nodes you can have? 0. Correct. So again, this the extreme case becomes our linked list example where there are no full nodes. Correct, and therefore this minimum number is going to be 0. The maximum is going to happen in the other extreme, which is going to be approximately, I mean, let's say floor of n by 2. Right. And this I'll leave for you to figure out, that the number of full nodes plus 1 is equal to number of leaves in a non-empty binary. Right. So number of full nodes, we understand that each node has 2 children, right? So those, count those nodes. that plus 1 is equal to number of leaves. Right? So this is one relationship which is also a property of a binary tree. And just to give you a hint, you can possibly make use of number of null pointers here and you will get that. Okay, so one specific application of trees, binary trees rather, is going to be in expressions, where expressions involve only binary operators. Right? So our plus minus star slash, this expression turns out to be a nice example of this, which can be nicely represented as an expression tree. The advantage of expression tree is again that you need not worry about parentheses. The precedence is already encoded in the expression tree itself, which means that B star C should be evaluated first before A plus happens, right? Because it is at the below plus, right? So it is a child of plus, star is child of plus, and therefore that should happen first. Similarly, star should happen first, then this plus, and then this upper star. So that is the, and in the end we will have the root evaluated, right? So this becomes a nice encoding of the expression trees. But it's not only the representation that is useful here. The idea behind expression trees also, which actually gets used in compilers, is that you can actually now transform the tree for optimization. Right? So if you have certain algebraic properties satisfied, you will be able to rearrange the nodes. For example, I mean, I'm just taking an example. It's not really an optimization, but let's say that there is B and C. If it so happens that instead of doing B star C, I would like to do C star B. That is easily possible when you have this expression tree. I just interchange the left and right pointers, and that is going to give me the commutativity property of star, exploiting the commutativity property of star. So this is not really an optimization, but you never know. So in such cases, transforming a tree turns out to be useful, and which is difficult to do on strings, right? So if I say that, okay, find out where variable D exists, and then variable E, and then there is a star in all of that. So all of that becomes a little clumsy because we are dealing with strings when we are dealing with the input expression, right, which is coming as a source code or maybe an intermediate representation. But in case of trees, it turns out to be relatively easy because you have already done the parsing. Right? Not that you will avoid parsing, you will have to still parse this, you will have to still parse this, but once you have it in this form, it becomes easier to process. All right, so the parenthesis went away because we have encoded the precedence already in the evaluation order, right? In some sense, bottom-up order. So here, D star E plus F, right? This can be parsed in two different ways. First, we do D star E, and then we add F. Alternatively, I can do E plus F, and then D star of that in absence of parenthesis, right? That is not possible in the expression tree, similar to the postfix notation. So there is going to be exactly one order. Okay, so can we write the expression itself in a way that no parentheses are required? Well, we have seen that in terms of postfix notation, and that gives us some sort of a, like I was mentioning some time back, that there are ways in which you can traverse the nodes in terms of postfix form, right, or prefix form, and that will give you a pre-order or post-order traversal, and we are going to study exactly that now. For example, in this case, if this is the expression A plus B star C, right, that is going to be encoded as this particular box, right? And I can say that the prefix notation is going to be plus A star BC, right? That is going to be a prefix form. And if you look at this plus A star, sorry about that, and then B C, this is the prefix notation. If you do a pre-order traversal of this subtree, which is rooted at plus, what will you get? You will get pre-order, which means that you have to first print the node. So you will print plus, then you will go to the left child, you will print A, then you will go to the right child and you will print it. So you will print star, then B, and then C. and exactly you will get the prefix expression. So if you convert your expression into an expression tree, binary tree, and perform a pre-order traversal, you will get the prefix code of that expression. In a similar manner, if you do a post-order traversal, you will get the postfix of that particular infix expression. I hope you found that interesting. So the pre-order traversal says, since we are talking about um, only the two children, what is this NLR? Can somebody guess? Good. So Andrea, Rishabh, Manichandana, Adarsh, Yashwant, and Shreya, all of them have suggested node, left, and right. So we first print the node, then we go to the left child, then the right child. But the pre-order traversal or prefix postfix, these are generic, these are not specific to binary trees. But there we could not talk about left and right children, right? So there will arbitrary number of children. But now in case of binary trees, we can say left and right, and that's what is the pre-order node. Then print the left subtree in pre-order form, then the right subtree in pre-order form. Similarly, postfix is or post-order traversal is going to be left child, right child, followed by the node. At the end, you do the node, that is post-order, and in order is left followed by the operator, which is the node, and then the right child. Any questions on this form? So as you can see that our prefix, postfix, and infix were different expressions, right? We talked about those in the context of stack. But now we are able to connect our tree representation with that data structure, right? So this connection is very important in data structures and in algorithms, where whatever we are studying in a different context, can you map it to something else which is probably arbitrarily different, right? So that those connections are really beautiful, not only in data structures and algorithms, in other places also, but definitely here. All right, so Inorder traversal is going to be essentially, we have seen the pre-order traversal where we said that RR arrow print, right, and followed by RR arrow left, RR arrow right. But now Inorder is going to be that printing is going to happen in between the left and the right, right? So that is what is our Inorder, between left and right. So as you can see, you just reorder these three statements and you get pre-order, post-order, and in-order. Any questions on this part? Okay, so let's do that then, right? So we have this code which is going to do give you in order printing of this expression tree, right? So if I run this code onto this tree, what is the output that I get? This is the same tree that we had earlier. Okay, Shania says, how do we do in order iteratively? Good question. Any suggestions on Shania's question? Because for uh, pre-order, we could use some sort of a stack, right? How do we do the in order? Where do we need to store this information? So we have two questions. One is, what is the output of this in order traversal? That is the code that is given on the example tree that we have. The second question is Shania's question, that if we have to do iterative in order traversal, how do we do that? So let's answer Shania's question first. So let's understand it in the context of this particular example, okay, that we have on the screen. So we are going to start with root. So let's say that I push this node to the stack because I can't print it right now. I go to its left child. Right? The left child again I cannot print, and therefore I push it again onto the stack. Then I go to its left child and I find that it does not have any children, and therefore I print it, right? So this gets done. Then I pop the whatever is on the stack. That is one way in which that can be done. And I print it. So this also gets done. And then I start, either I push the right child of that, or I start processing the right child. So I reach here. This right child has, so this currently the stack contains only this, let's say. Now this particular node does have children, so I can't print it now. So therefore I push it to the stack. At this stage, I am going to go to the left and print this since it does not have any children. Then I go back, I print this, pop it from the stack, and since I have completed processing of its left child, I'll print it and push the right child. When I pop, he does not have any children, and so on, right? So one way of doing this is again using a stack, where you will have to not remember, but that will come in easily in the code, because I can distinguish between whether I'm processing the left child or the right child. So I can push the appropriate code there. That is one way. The second way is that when I push this node, I first push the right child, then I push this node, and then I push the left child, or start pressing the left child. Right? So that makes sure that the right child is going to get processed in the end after the node is processed. Right? So that is another way in which that gets done. But essentially that means that you can use a stack to do an in-order traversal iteratively. Kasibhatla is using stack. We can convert recursion to iteration using stack. Yes. So one of the issues that can come up, and that probably originated Shania's question, is that do we require two stacks? One for the left part, another for the right, because we have two in-order traversals coming at two different places. Thankfully, in this case, it doesn't happen, and you can perform it using a single stack. The order can be first push the right, then push the node, and then push the left, so that we pop it in the appropriate order. But in some other recursive mechanisms, it's possible that you might have to maintain multiple stacks. Shania says, okay, Shania has given the output of this. Anybody else wants to give the output? Okay, so did we get the expected output? See, essentially we started from an expression, right, which is given in the source code, which we converted into an expression tree. And now if I do an in-order traversal on the expression tree, I should expect that I'll get the original expression. Did we get the original expression? No, right? Okay, so I hope you guys agree with that. So only doing an in-order traversal will not give you exactly the expression, and require something more to get that expression. What is that? Right? So our infix form is inherently ambiguous. Our infix form is inherently ambiguous, which is what the in-order traversal is going to give you. Expression tree is not ambiguous. The current expression tree is not ambiguous. It has a fixed order in which the operators should be evaluated. But the infix form is, that is the when I write the using symbols in a string, that is ambiguous if you do not use parentheses. So disambiguate that, we need to add parentheses as soon as we add the expression. So this is going to be actually B star C should be put in parentheses. Then A plus B star C should be put in parentheses. Then D star E should be put in parentheses. Then D star E plus F should be put in parentheses, and so on. Right? So all of these parentheses should be added as and when we come to an operator, and then it will become exactly the same expression. Might have some additional parentheses, but at least it will be unambiguous. Right? All right. So this is what we get, as Shani has also suggested, and the actual expression was something different. Right? So we have to worry about those parentheses carefully. Okay, sounds good. So this should be understood. Any questions so far? All right, so we'll move ahead. I'll just quickly show post-order traversal. It's been a while since we looked at the code. Let me just do that. So I'll have to unshare this. Okay, so I hope the screen is coming up for you and you are able to see the code. So I think the initial part we know of using the type def, and in this case I'm defining string as a data type for individual nodes data. Yeah, this part we have looked at, add child and print. So node is okay. The tree is going to be again similar, in order, post order, etc. We had pre-order also earlier. So let's look at in order traversal. Essentially, I need to print opening and closing parentheses that will make it unambiguous, and then the rest of it remains the same as we have seen. Post-order traversal remains exactly opposite, and we don't need to worry about the parentheses. But we we process the left child, then the right child, and then the node. Right. So left, right, and node. LRN is the post-order traversal. Create node remains simple. Yeah, so let's look at main first. So I'm going to create that expression tree using create node and add child. Right? So create node just creates a particular node. So we require all these nodes to create that expression tree, and then we are going to add the child of appropriate nodes. It turns out that add child takes care of adding the node. I mean, I'm not specifying add left child and add right child. So it so happens that the way it is written, if the children get added from left to right, that is, if left child is empty, that is null, then I'm going to add it there. If left child is non-empty or non-null, then I'm going to add the right child, right? So that gets automatically done, as you can see the add child implementation here. So if left is non-null, then I add it to the right child. Otherwise, I add it to the left child, right? So that takes care. I don't have to worry about left child and right child while calling the API. But that also reduces the number of trees that you can create, right? So I cannot create a tree which has only right child, right? In this expression tree, it doesn't happen. Therefore, we have that. Otherwise, we will require that particular API to be provided. All right. So let's see if we can compile this and run it. So I have created that expression tree whose post order traversal turns out to be ABC star plus. Is it turning out to be that? Let me just quickly check. A B C star plus, that is correct. Then DE star F plus, DE star F plus, then G star plus, G star plus. Yeah, so you are not able to see the expression tree. I'm able to see that on the slides. So that seems to be correct. That seems to be all right. Okay. Any questions so far on the code? Anything related to C++? As you can see, the expression tree that we have created is manual. So I created individual nodes and then I added some edges into it, and that is really cumbersome. Ideally, I should, and this code is not going to work for any other expression tree. I'll have to change the program to create another tree. So it would be nice if I can have the expression given to me as an input and I create an expression tree out of it. And then I perform a post order traversal of that and print it, right? So that will be much more useful. So since there are no questions, I'll go back to the slides. Okay, so our post order traversal looked similar. And then for this, yeah, we should have gotten this. That is what we got it. And operator precedence was encoded in this. This we have done infix, prefix, postfix. So I'm just going to show that. And we also noted some properties that the order of the operands, that is the A, B, C, D, this remains exactly the same in infix, prefix, and postfix. And the operators in prefix versus postfix are in opposite order. Right? If this is plus plus star or plus 1 plus 2 star, this is going to become star plus 2 plus 1. Okay, any questions on this form? All right, so we'll move ahead from here. Evaluating postfix, that is, you are given a postfix expression and you are evaluating it, that we have already done. And therefore we can just skip this. We used a stack and evaluated this. We pushed the operators in the stack, and whenever operands on the stack, and whenever we encountered an operator, we popped two values and evaluated the expression and pushed the value back. Right? So this was all done. That is not an issue. This is what one of the things that can come up. So we thought about that it would be nice if I can give you an infix expression and convert it into an expression tree. That we are not doing, but what we are doing is, given a postfix expression, can you convert it back to a tree? So far what we did was, we given an expression tree, convert it into a postfix. Now I am trying to do the opposite. Please think about if you are able to do that. Any suggestions in this regard will be helpful. Murari says it's like given a post order traversal, construct a tree. Yes, you are given the left hand side post order postfix notation expression. We would like to construct the tree. Yes, correct. Any suggestions? Okay, so since no suggestions are coming, I'll mention this. So this is going to be Andrea says keep putting into stack where when reach operator. Okay, pop two elements. So this is similar to postfix evaluation, right? So you are given a postfix expression and you want to evaluate it. What do? We say that okay, A is coming, A is an operand, let's push it to the stack. B is an operand, push it to the stack. C, push it to the stack. And then star comes to pop two elements and evaluate and push the result back. Instead of that, what we will do is pop the two elements, create a subtree of these two. So star, B and C will be the two children of that in appropriate order, the way Murari has written, and push the pointer to the star node back into the tree, back into the stack. So when ABC come, we push its create nodes, I mean the nodes corresponding to ABC into the stack. And when star comes in, it pops B and C's nodes, attaches those to the star, creates that subtree of B star C, and then pushes back the root of this subtree, which is the star's pointer, so that the stack now contains A's pointer followed by star's pointer. And now when plus comes in, essentially you have these two children of plus available, and you create that subtree rooted at plus, and then push the result, I mean the pluses pointer into the stack again, and in a similar manner you evaluate the right subtree of the root plus. So what Andrea and Murari have suggested, that seems to be on the right lines, where you are actually evaluating in some sense postfix form, right? Exactly the same algorithm will work, just that instead of working with numbers, you will now probably work with the pointers to each of these variables. All right, I hope this concept is clear. In case it is not clear, please let me know. So exactly similar way that we have done that code, where push its node to the stack and pop two nodes from the stack and push the root, right, after creating that subtree. Right. So we have this postfix to tree.cpp. I'll go through it maybe in the next class. I'll stop here for any questions. We'll look at the code in the next class. Andrea says, can we do recursive without storing the string? Storing the string meaning? I didn't understand the string part, Andrea. If we process the postfix from left to right, yes. I mean, we need not store the string. Yeah, that is, we need not store the string. As and when the elements are coming in the input, we can continue processing. That is possible. Yeah, we need not store it in a string. That is possible. But that need not, can we do it recursively? Oh, I see. Without using a stack, you mean? I think that is possible. So instead of, so that is possible. Instead of using the operand stack, we can store that operand in a local variable and call the same function recursively with the next element as the input, right? So the input, let's say, is going from I equal to 0 to n minus 1. You can call it with I plus 1, and that will take care of the next element to be processed. And once you have the sub expression done, then we return to this caller where you have that value stored as an operand, right? So that seems to be all right. There is a small catch. We'll have to model how to pop the elements from the stack, because we'll have to pop it twice. So I think that needs to be taken care of by pushing by pushing the elements to two arguments and modifying those arguments and returning, right? So that is possible. I have not tried it, but I think this is doable. This is doable. That's an interesting question. Um, yeah, Murari says one early request: when we have quiz 2 in the afternoon, some students have lab and some of us have a class in the morning. Uh, sure, I think this request has come up pretty early. So we have our quiz 2 planned on October 9, right? And it should be Saturday, right? And earlier we had planned for 10 o'clock. Can we have it, let's say, at 3 o'clock? Right, so I'll just write it: quiz 2 on October 9 at 15. Anybody has any objections to this? So it will be again similar to quiz 1, where you will, I mean, you'll be given approximately 90 minutes or so, depending upon how the paper shapes up. Okay, nobody at least present here seems to have any objection. I'll anyway post it on the Google group, so that Shania says, could we get practice questions like was discussed after quiz 1? Yes, we will do that. I think this suggestion had come up just after quiz 1 also. Okay, so let's see. We have October 9, right? So we have a whole of that week, 4, 5, 6, 8. So maybe on 6th or 8th, we will have some sort of practice questions which we can discuss, so that you get some feel for the questions for the quiz. Sure, we'll do that. I'll post this information. Thanks for reminding. Any other concerns, questions? I'm glad that you guys have started thinking about the quiz already. All right. So if there are no further questions, then we will stop here. Let me stop the recording.